Far out in space, roughly 1,000,000 miles from Earth, at a delicate gravitational balance point known as the Sun-Earth L2 region, the James Webb Space Telescope is doing something far more extraordinary than simple observation. It is not just pointing into the cosmos. It is effectively looking back through time itself, capturing ancient light that has traveled across billions of years to reach us. Each faint signal it detects is not current information, but a relic from a universe long gone. Some of these photons began their journey more than 13 billion years ago, carrying evidence from the earliest stages of cosmic existence. Yet what they reveal is not the slow, predictable unfolding of structure that scientists once expected. Instead, they are showing hints of a universe that became organized and complex far earlier, and far faster than traditional models suggested. For many years, the standard understanding of cosmic evolution followed a gradual path. In the aftermath of the Big Bang, the universe expanded and cooled. Matter was spread almost evenly, with only tiny fluctuations in density. Over time, gravity began to amplify these small irregularities, pulling gas into vast halos of dark matter. Slowly, over hundreds of millions of years, the first stars were born inside collapsing clouds of gas. These early stars then produced heavier elements, died, and seeded future generations. Galaxies formed through repeated mergers and long cycles of star formation, eventually building the large cosmic structures we see today. In this view, the early universe should have been relatively simple, small, dim, and only beginning to organize itself. That expectation is exactly what the James Webb Space Telescope was built to test. But as Webb peered deeper into the infrared universe, reaching further back in time than any previous instrument, the picture began to shift. Instead of a young cosmos filled only with faint, primitive galaxies, it started revealing objects that appear unexpectedly developed. Some galaxies detected only a few 100 million years after the Big Bang already show surprising size, brightness, and structural complexity. These are not minor deviations. Some of them contain hundreds of millions, even billions of stars, arranged in shapes that resemble far more evolved galaxies like our own Milky Way. Their existence introduces a clear tension between observation and theory. According to established models, galaxies should require much more time to reach this level of maturity. This has led scientists to carefully describe them as unusually advanced for their epoch. While not a violation of known physics, it does suggest that something about early cosmic growth may need refinement. Naturally, researchers first examined possible observational effects. Could gravitational lensing be amplifying their brightness? Could dust or measurement errors be distorting distance estimates? Some corrections were made, and a few extreme cases were adjusted. But even after these refinements, the overall trend remains. There still appear to be more mature galaxies in the early universe than expected. As this pattern persisted, attention expanded beyond galaxies themselves to something even more extreme: supermassive black holes. Many of these early galaxies host black holes with masses millions or even billions of times greater than the Sun. According to standard growth models, such objects require long periods of gradual feeding from surrounding matter. Even under optimal conditions, their growth should be limited by physical constraints such as radiation pressure. Yet Webb has identified extremely bright quasars existing when the universe was only a few 100 million years old. These black holes appear far too massive for the time available. This creates a second major puzzle. Either black holes in the early universe grew much faster than expected, or they formed through alternative mechanisms, perhaps direct collapse from massive gas clouds, bypassing normal stellar evolution altogether. Neither explanation is fully resolved. The story becomes even more intriguing when looking at the large-scale structure of the universe. Galaxies are not randomly scattered. They form a vast interconnected pattern known as the cosmic web, filaments of matter stretching across enormous distances, meeting at dense clusters and separated by vast empty voids. This structure was thought to develop slowly as gravity gradually shaped matter over billions of years. However, Webb's deep observations suggest that elements of this network may have formed earlier than predicted. Some galaxy groupings already show signs of interaction and clustering at very early times, hinting that large-scale organization began sooner than expected. In some regions, galaxies appear not just present but already dynamically linked, as if gravitational structures matured rapidly in the universe's first stages. Another unexpected clue comes from star formation itself. Certain early galaxies show signs that their star-forming activity had already slowed or stabilized. This suggests they may have gone through their major evolutionary phases in a much shorter time than models allow. Instead of a slow build-up, some systems appear to have developed, matured, and settled remarkably quickly. This has led scientists to reconsider deeper physical processes that may have influenced the early universe. Dark matter, which acts as the invisible framework for galaxy formation, may have behaved differently under early extreme conditions. Its distribution could have accelerated gravitational collapse more efficiently than current simulations account for. Some more speculative ideas have also resurfaced, ranging from unusual early cosmic structures to unknown feedback mechanisms that might have triggered rapid bursts of star formation. While none of these ideas are confirmed, they highlight the growing complexity of the puzzle. Adding to this mystery is the chemical composition of these distant galaxies. Webb has detected unexpectedly rich amounts of heavier elements in some of the earliest systems observed. Since these elements are formed inside stars and released during supernova explosions, their presence implies that multiple generations of stars must have already lived and died in a relatively short span of time. This compresses the timeline of stellar evolution far more than previously thought. When all these observations are viewed together, a consistent theme begins to emerge. The early universe may have been far more active, efficient, and structurally advanced than the slow and gradual model once proposed. However, this does not necessarily mean existing cosmological theory is wrong. Instead, it suggests that the earliest stages of cosmic history may need refinement. The Big Bang framework still holds, but the details of how matter transitioned from simplicity to complexity may involve faster and more dynamic processes than previously understood. Importantly, the James Webb Space Telescope is still in the early phase of its mission. It has only observed a small fraction of the sky at its deepest sensitivity. With each new dataset, it continues to push further back in time, closer to the universe's first moments of structure formation. What lies ahead could include even earlier galaxies, more extreme black holes, or entirely new categories of cosmic objects that have yet to be explained. Ultimately, the telescope's greatest contribution may not be a single discovery, but the transformation of our questions. It is revealing a universe that seems to have organized itself with surprising speed in its earliest chapters. And as more ancient light continues to arrive, one idea becomes increasingly difficult to ignore. We are not just filling in gaps in an existing story. We may be witnessing that story being rewritten, slowly, carefully, and continuously, by every new photon arriving from the beginning of time. As the James Webb Space Telescope continues its silent survey of the deep universe, the picture it is building is becoming increasingly difficult to treat as a collection of isolated surprises. Instead, a pattern is beginning to emerge, one that suggests the early cosmos was not just active, but possibly operating in ways that compress time itself in terms of structure formation. The further Webb looks back, the less empty the early universe appears. Instead of a slow transition from darkness to structure, the data increasingly shows a universe that seems to switch on with surprising intensity. Galaxies appear earlier than expected, black holes reach extreme masses far too soon, and chemical enrichment shows signs of rapid progression. It is as if multiple layers of cosmic development are unfolding simultaneously, rather than step by step. This raises a deeper question that scientists are now carefully exploring. Was the early universe truly slower and simpler, or have we underestimated how quickly complexity can emerge under extreme conditions?